Okay, welcome to lab. We'll get started here in just a second. So again, we're doing study assignment F, I believe. We'll get started here in just a second. Okay, so today up on tap is, I believe, study assignment F. So study assignment F, which is redox reactions. So we're talking about redox reactions in lecture, and we talked about how to balance sort of basic redox reactions. And in this study assignment and in future ones, you'll have to sort of do a little bit more complicated balancing of these redox reactions. So we're going to go over how to properly balance these guys in both acidic and basic conditions. So it's a little bit more entailed than just sort of making sure the electrons are the same and all that kind of stuff. And then obviously you could get onto it and do it. Like I said before, sort of schedule-wise, we're going to do this one today. Tomorrow we will do the experiment that was scheduled today, which I believe is the reduction of iron. And then on, that takes us to Wednesday. On Thursday, we will do the study assignment that was for on Wednesday, which is the stoichiometry study assignment. So we'll do this one today. We'll tomorrow, I think it's experiment 9. It has to do with iron, I think, oxidation. And we'll do that on Wednesday. And then I believe it should be study assignment G at that point, which should be stoichiometry. On Thursday. And then starting next week, we'll get into the titration experiment, which is a big experiment. That should be experiment 10, I believe, if I'm not mistaken. So we'll just move that. So I think technically we're supposed to start titration on Thursday. We'll just move it to next week. That'll be plenty of time. That's more than enough time to sort of do that experiment and watch those videos. So that sort of is the schedule here for the rest of the week and then into next week and sort of that adjustment. So basically just, if you look at the schedule, just move everybody over one in terms of the lab part. All right, so today we're talking about redox, and as we talked about, oxidation means that typically something has lost electrons, and reduction means that something has gained electrons. And remember that we also talk about oxidizing agents. And remember that the oxidizing agent is the substance that gets reduced. So the guy that goes through reduction will be your oxidizing agent, while your reducing agent is the opposite there. It is the substance that gets oxidized. So the reason they're named or opposite of that is because they basically cause that to occur in the opposite sort of location. So the oxidizing agent causes the oxidation of somebody. Because he causes the oxidation of somebody, they're going to lose electrons and it gets reduced, and vice versa. The reducing agent causes something to go through reduction, which means something gets to gain electrons. In order for it to gain electrons, it themselves have to be oxidized and lose those electrons. So in a sort of basic sort of balancing of equations, if you had something like magnesium goes to magnesium 2 plus 2 electrons, and you had something, let's say, like Cl2 plus 2 electrons, 2 Cl minuses. These would be what are referred to as half reactions, as we talked about. This would be our oxidation half reaction. And we know it's the oxidation half reaction because we see the electrons on the product side, like they're being given off or lost. This would be our reduction half reaction. And we know that's the reduction half reaction because we see the electrons on the reactant side like they're being gained. And when we take our half reactions, we essentially add them together. And when we add them together, what always needs to happen is the electrons do need to completely cancel out. So they're on opposite sides of the arrow. So they will completely cancel out, and we'll be left with the overall reaction here of magnesium plus our chlorine gives us our magnesium chloride on this side. And this would be our overall reaction. Everybody on the left-hand side stays on the left. Everybody on the right-hand side stays on the right-hand side. Now, if we had two half reactions where the electrons were not the same, you would need to multiply one of the half reactions by a number to make sure that you end up with the same number of electrons in each half reaction. Remember that an oxidation reduction reaction always occurs together. And what that means is it will always happen if something gets oxidized, there should be something that's getting reduced, and the total number of electrons that get transferred should be the same. And that's why in these half reactions, they should always be the same. We also can look at this overall reaction here and think about oxidation states like we talked about. This guy would have a 0 oxidation state and a standard state uncombined. This guy would also have a 0 oxidation state. The magnesium here, when it hooks up with the chlorine, becomes +2. The Cl is -1. So again, we could use something like that number line that we talked about to figure out what is being oxidized and what is being reduced. Remember, if you go through oxidation, you become more positive. If you go through reduction and gain those electrons, you become more negative. So if you look at the magnesium, it started at 0 and ended at +2, so it's heading in this direction. So the magnesium here, as we can see, is going through oxidation, while the chlorine also started at 0, but ends up at -1, which is heading in that direction to the left, and it's going through reduction, which we also see as well. So these are all the things that we sort of talked about in class. Any questions on this part of it here before we get into the little bit more complicated aspect of it? Okay, so let's talk about how you balance a little bit more complicated redox reactions in acidic or basic medium. So we can balance these guys in either acidic or basic conditions. So we're going to talk about how to do it first. We'll do both, but we're going to start with acidic. So if you are asked to balance a redox reaction in acidic conditions, these are sort of the steps that you want to follow. So let's take a look at an equation here. So we have Fe2 plus Cr2O7 2- goes to Fe3 plus and Cr3 plus. So the first thing you want to do if you're given an equation like this is to basically separate out each of these guys into their half reactions. And the way you do that is pretty simple. You just find the two things that obviously look alike, What I mean by that, obviously iron and iron are related to each other. So 1/2 reaction would be the iron 2 plus going to the iron with a 3 plus, right? Obviously, this has chromium in it. This also has chromium in it. So our other half reaction would be the ones that have chromium in it. Right? Now, we could also use our oxidation numbers to help us understand what is happening here. So the oxidation state of the iron is +2. The oxidation state of this iron is +3. So when we think about what is happening here, again, if you're not sure, you could use that number line. The iron started at +2, which is here, and ended at +3, which is going in this direction, which means that it is going through oxidation. So this here would be our oxidation half reaction. We could also look at the chromium here. The oxidation state of oxygen is -2. There's 7 of them is -14. The overall charge is -2, and there's 2 of these. So just like we did, I actually think we had this guy in an example. The oxidation state of the chromium there is actually going to be +6. Oxidation state of this chromium is +3. Again, if you're not sure what's happening, you can see that the +6 would be down in this region, and it's heading down this way to our +3 in that direction, which means it's going through reduction. Again, if you go this way, it's oxidation. So this would be our reduction half reaction. Again, you could determine that by figuring out one of them. So if you figure out the oxidation, you know that by default the other one's the reduction, and vice versa. So that's good to understand, what each of those guys, what's happening in each of those, because it will help you as you go through sort of the process to balance these and hopefully end up with the right thing. All right, so once you sort of determine what is going on in terms of who's being oxidized and who's being reduced, and once you basically have split it off into its 2 half reactions, the next thing that you want to do is balance every element except oxygen and hydrogen. So we want to balance everybody except oxygen and hydrogen. So when we look at the iron, we have 1 iron on the left and 1 on the right. So in terms of numbers of elements, we're good. We don't have to worry about it. When we look at the chromium here, we have 2 chromiums on the left and only 1 chromium on the right. So we need to balance the chromiums just like we would balance an equation, and we would put the 2 in front of it. And when we put the 2 in front of it, we now have 2 chromiums on each side, 1 iron on each side. So now everything is balanced except for oxygen and hydrogen. Now to balance oxygen, the way that we balance oxygen is, make some room over here perhaps. Use this spot up here. A little bit of racing. So to actually balance the oxygens in this sort of method, what we use to balance oxygen is actually we use water. So we add water to whichever side needs the oxygen. Now, the important part about when you add water to balance out the oxygen is when you add the water, you're not really just adding oxygen, you're actually adding H's. So for every water that you add to one side, to the other side, you need to add 2 H pluses. So whichever side needs the oxygen, you add the appropriate amount of waters. And then for every water that you add to the opposite side, you add 2 H pluses to balance out the hydrogen. So to see how that works, in the top one, there is no oxygen, so we don't have to worry about it. In the bottom one here, we have 7 oxygens on the left, 0 on the right. So to balance that out, we would put 7 waters over here on the right-hand side. Now, because we put those 7 waters, we need to add 14 H pluses to the left-hand side. And the 14 H pluses is to take care of the 14 hydrogens that we added. So one side gets water that needs the oxygen, the other side will get the H pluses, and again, you should be balanced. The ultimate goal here when we're done balancing this is it does need to be balanced two ways. It needs to be balanced like a traditional chemical equation, which means you have the same number of elements on each side, which is why it's important here that we put the H pluses in so we have the right amount of hydrogens. And secondly, when it's all balanced, the overall charge on the left-hand side of the arrow needs to equal the overall charge on the right-hand side of the arrow. They don't have to equal 0 on both sides, but they do need to equal the same number. So after we have balanced all the other elements, after we've added the water to balance the oxygen and the H plus to balance out the hydrogen. And by the way, if at some point you started out in a half reaction with more hydrogens on one side than the other, you could just add H plus to the other side to balance it out as well. Once we've done all that, the next thing that we want to do is balance out the charge on each side by adding electrons. So since electrons are negative, the goal here again is not to get each side equal to 0, but to get each side equal to the exact same charge. The easiest way to do it is just to look at the overall charge on each side of the arrow. So let's take the top one, for example. Overall charge on the left-hand side, there's +2. Overall charge on the right-hand side is +3. What that means is the top guy needs 1 electron on the right-hand side. +3 and -1 gives you +2 on the right, balances out with the +2 that we have on the left-hand side. So we put our electron over there on the right-hand side. On the bottom half reaction, 14 times +1 is +14. This overall thing is -2, which means overall charge on the left-hand side is +14 and -2 is +12. On the right-hand side, the overall charge is +6. That means to balance it out, we would need 6 electrons over here on the left-hand side. -6 from the electrons, -2 from the dichromate is -8, and +14 is +6 on the left, +6 on the right, and we're balanced in terms of that. Any questions on adding the electrons there? So again, the goal here is to add the electrons to balance the charge on each side. Again, that charge does not have to be 0. Just needs to be the exact same total number of charge on each side. We could also verify that we did not screw up by looking at what we're doing here and thinking about what we figured out earlier. Earlier, we figured out that the top reaction, the iron one, was the oxidation half reaction. And what we know about oxidation half reactions is the electrons should end up on the product side, which they did, which is good. We also know that the bottom one was the reduction half reaction. And what we know about the reduction half reaction is they should end up on the reactant side, the products. So we did add the electrons to the correct side based on what we know, and that's a good way to check yourself. The electrons should always end up being on opposite sides of the arrow. If you add electrons to the same side of the arrow in each half reaction, something is definitely wrong. So you should never add electrons to the same side. They should always be opposite sides. And the reason for that is they need to completely cancel out. So the next step would be add both of those reactions together. But before you add together, you need to have the same number of electrons in each half reaction. So in the top one, we only have 1 electron. In the bottom one, we have 6 electrons. So for the top one, what we need to do is multiply not just the electrons, but everybody that's there by that number of 6. And that should get us all to the same number of electrons. So I'm just going to rewrite this, guys. So I'll put a little line here. I'm going to rewrite it underneath with the 6 being distributed. And if I do that, that will give me 6 of the iron 2s goes to 6 of the iron 3s and our 6 electron. So again, I just distributed my 6 across there. Now that I have 6 electrons in each half reaction, I can now add these together. When I add half reactions together, basically everybody on the left-hand side of the arrow stays on the left-hand side. Everybody on the right-hand side stays on the right-hand side. So that's going to give me 6 electrons plus 14 H pluses plus Cr2O7 2 minus plus 6 of the iron 2s. That takes care of everything on the left-hand side of the arrow. On the right-hand side of the arrow, we got 2 chromiums plus 7 waters plus 6 irons with a plus 3 charge and 6 electrons. Now what you can do is anything that is the same on opposite sides of the arrow, you can either completely cancel out if they do or reduce down. So if we look, we see we have obviously what should always happen. The electrons should completely cancel out. And at that point, I think that will be all that I got going on there. Hang on a sec here. There you go. So that should be nothing else canceling out. So we should have 14 H pluses plus Cr2O7 2 minus plus 6 Fe2 plus 2 Cr3 plus 7 waters and 6 of these guys. Now, if I did everything correct here and I didn't really mess up anything, this should be balanced in acidic conditions. And we could check it when we look at it. What we're looking for is we're looking for it to be balanced both ways, like I talked about, both in terms of numbers of elements on each side and overall charge. So if we look at it, we have 14 H pluses on the left, 14 H's on the right, 2 CRs on the left, 2 CRs on the right, 7 oxygens on the left, 7 times 1 is 7 on the right, 6 irons on the left, 6 on the right. So it is balanced in terms of a regular equation, the exact same number of elements on each side. It is also balanced in terms of charge, hopefully. So on the left-hand side, I have plus 14 for the hydrogens. I have plus 12 for our iron. So that's a lot there. We're going to try that math. That's plus 26 minus 2 is plus 24. So if you add up all the charges on the left-hand side, plus 24. On the right-hand side, 2 times 3 is plus 6. 6 times 3 is plus 18. So that's 18 and 6, which is plus 24 on the right. So overall charge plus 24 on the left, plus 24 on the right. Everything's balanced. Everything's balanced in terms of elements as well. Question on that there. So the steps to balance an equation in acidic conditions, split off into half reactions, balance every element besides oxygen and hydrogen, then balance oxygen by adding water, and then H plus to the other side to balance out the hydrogens. Then you want to add your electrons to each half reaction to balance out the charge. And then you want to combine the half reactions, cancel out the electrons, should always be gone. And then whatever else may cancel as well. And then you should be balanced in terms of acidic conditions. Any questions on those steps? Now, for basic conditions, there is a couple ways to do it, but the easiest way to do basic conditions, I think, is to do exactly what we just did. So you could do exactly what we just did, pretend that you're balancing the equation in acidic conditions, But if you're going to do basic conditions, once you get to the end, so once you get to that equation that's in the box, I'm just going to rewrite it here so I have it to look at. So we had 14H pluses plus Cr2O72 minus plus 6 iron 2. On the other side, 6 of the iron 3 and 2 of the chromiums and 7 waters. Okay. So this again is what you would get, obviously, like we just did there for acidic conditions. If this is basic conditions, what you do at the end is once you have this equation, there will be a side that has H plus in it. And the number of H pluses that you have is the number of OH minuses you should add. And the deal here, though, is you're going to add it not to just one side, but you're going to add the OH minuses to both sides. So here in our example, I would add 14 OH minuses. And again, the 14 comes from the amount of H plus that I had. And when I do again to both sides, and the side that has the H plus and the OH minus that you added, H plus and OH minus basically make water. So these guys will come together and make 14 waters. And everything else here will be the same. And usually when you do this and you get to this part, there usually will be some waters that you can reduce. So if you look on the right-hand side, I have 7 waters. On the left-hand side, I have 14 waters. So I could get rid of 7 waters. So I would be left with 7 waters on the left. It's kind of like a math when you subtract like the X over there to the other side. Yeah, so the reason I put 14 OH minuses is it has to do with the amount of H plus that you have. So in our original equation when we started, after we balanced it in acidic conditions, we were left with 14 H pluses. So if you need to balance it for basic conditions, it is the total number of H pluses you have is how many OH minuses you should add. And again, you add it not to one side, but you add to both sides. So that's why we added 14 OH minuses, matches the H plus that we started with. So after I reduce that down, we end up with this equation. And I think that's all that should reduce down. And now, if I did not screw up again, hopefully, we should still be balanced both the same way in terms of numbers of elements on both sides and also the charge. So over here, 14 H's on the left, 14 on the right, 7 oxygens there plus 7 more is 14. So 14 oxygens, 2 chromiums, 6 irons, 6 irons. Now, overall charge here on the left, we have -2 from this guy and +12 from this guy. So that is a +10 on the left-hand side. On the right-hand side, we have 6 times +3, which is 18, plus 6 more, which is 24. And then we have 14 times -1. So that's +24 minus 14 is +10 on this side and a +10 on this side. We're balanced in terms of the charge and also the element. So this would be the balanced equation in basic conditions. And that really is sort of the easiest way to do it. Just balance it like acidic conditions, and at the end add OH minus to both sides, and whichever side has the H plus will make the water, basically. And then you can reduce down the waters. Question on that. We know this really is a basic equation because bases basically have hydroxide in it. So because this has hydroxide in it, we know we're pretty much doing basic conditions. Yeah? And that's also why when we looked at the one we did before, we didn't have hydroxide, we had H+, which tells us this is acidic conditions. Acids are basically H+, right? And bases have OH- in it. So this is the way that you can balance more complicated redox reactions. Again, acidic or basic, pretty much the same procedure. I would follow, again, do everything acidic, and then if it is basic, do this last step where you add the OH minuses to both sides. Again, the OH minus is equal to the number of H pluses that you have. Any questions on that there? Okay, so let's take a look, though, at a couple of little guys here from the actual study assignment, because there's kind of some weird ways things are worded, I guess, or put in there. There's reasons for it. So let's take a look at 1A, for example, just to give you an idea how to complete 1A. So we go here. So on study assignment 1A, what you are given is Cl, an old minus, I think, minus, goes to ClO3 minus. And in this question, you are asked, let's see what you are asked here. You want to, above each element, label the oxidation states. So we want to figure out the oxidation states on each of the elements that are there. You also want to identify the reaction as either the half reaction, that's oxidation half reaction, or the reduction half reaction. So in question number 1, you're really only dealing with one half reaction. So if you remember, there's the oxidation half reaction, reduction half reaction. In part 1 here, you just have one part of it. You have to determine, is it oxidation or reduction? And then you want to write the balanced half reaction to the right. And we're going to assume that it's acidic conditions. Okay, so let's just take this first one here and kind of go through all the parts of it so you know how to do the rest of them. So we will start with the oxidation states. So oxidation state of our chloride here is -1. Oxidation state of the oxygen is -2. There's 3 of them, right? Gives you -6. Overall, it's -1. So the oxidation state here, like we talked about in class, would be +5 in this case, right? +5 and -6 gives you -1 overall. So one of the first things you need to do is kind of like what I just did there. Above each of these guys, you need to write the oxidation numbers with the charges, obviously the minuses and positives. From just the oxidation states, we could look at the chlorine and figure out what's going on. Again, we're starting at -1 and we're ending at +5, which is in this direction. And again, going in that direction, that is an oxidation that's occurring, which means that this thing is a oxidation half reaction. Any questions on that? Now, the last thing that you're going to do is you're going to balance this in acidic conditions. So what we're going to do here is really what we were just talking about. We're going to take the Cl minus, the ClO3 minus, and to balance it, we want to make sure we balance all the elements except for oxygen and hydrogen. So we have chlorine and chlorine, 1 on each side, so we're good. To balance the oxygen here, we're going to add our water. So in this case, we actually need to add 3 waters to the left-hand side. That gives us 3 oxygens. Just like we talked about, when I add the 3 waters, I now need to add 6 H pluses to the other side. Again, that's going to balance out our H's. After I balance my oxygen and my hydrogens, I now could balance out the charge by adding electrons like we talked about a second ago. Overall charge on the left-hand side is -1 coming from the Cl minus. Overall charge on the right-hand side, this is -1. This is plus 6. Plus 6 and minus 1 is plus 5. So on this side, we have basically plus 5 overall. On this side, we have minus 1. Remember that to balance out the charge, we're adding electrons, which means the side on the right here actually needs 6 electrons. Because if I now add my 6 electrons, plus 5 and minus 6 gives me minus 1 and minus 1. So this right here would be your balanced half reaction that you would put on the line. It is balanced just like we did before. We have 6 hydrogens on the left, 6 on the right, 1 Cl on the left, 1 Cl on the right, 3 oxygens on the left, 3 on the right. Again, overall charge on the left, minus 1, overall charge, minus 1 on the right. Also makes sense because we identified this as an oxidation half reaction, and our electrons are on the product side, which is the oxidation side, right? Any questions on that? So number 1 on the study assignment, that's essentially what you're doing is you're just working really with one half reaction. And you want to kind of go through all the steps to balance that one half reaction. Obviously, we don't have the other part, so we can't add them together or anything like that. We just have the oxidation part here. Any questions on 1 there? No, I actually added the 3 water molecules to the left because when we originally started up here, we had 3 oxygens on the left. So that's what made the waters being added to the left-hand side. So you add the waters to the side that needs the oxygen. And because you added the waters, the process of adding those 3 waters to this side is we now just added the 6 H's. And that's why we have to add the 6 H's here to balance out the extra hydrogens we added when we added the water. Other questions on that? So I think you're asking about the electrons. So when we look at water on the left-hand side, there's no charge, right? So this is 0. This Cl minus overall is minus 1. So overall on the left-hand side, we had minus 1. When we looked on the right-hand side, this entire thing has a minus 1 charge, right? And we had our 6 H pluses, which has a plus 6 charge. That gave us a plus 5 overall. Yeah. So again, we want to get these guys to the same number, which means we have to add electrons, which are negative. And if we add only, say, 1 electron, right, that takes us down to plus 4. These two numbers don't match. So we got to get these numbers to match, basically. So when we add the 6 electrons, 6 negatives and 5 positives leaves you a -1 left over. And now the charge on each side matches. So the goal is when you're adding the electrons to get the actual same exact overall charge on each side. And in this case, -1 and -1 on each side is what you're shooting for. Obviously, because the other side was negative, if we added electrons to the left-hand side, we just become more and more negative and it'll never match. So the idea is to match the numbers on both sides, both the number and the charge, not add them together. Other questions on that? Okay, so that's pretty much number 1 there. You basically just want to get each of the half reactions balanced. Let's take a look at like number 2 or so. I guess that's all 2. So number 2, and sort of how things are written and why things are written and what you should do and kind of what you should ignore on this thing is, let's take a look at number 2A. So if we look at 2A, we have this equation given to you, MnO4 minus plus SO3 2 minus goes plus H plus. water, and SO4 2 minus and Mn2 plus. So this is the equation that you're given, and you want to balance it. Now, in this case, it didn't tell you, is it acidic, is it basic conditions? So they actually added some extra stuff into the equation to tell you that. But by doing that, they sometimes confuse people as to what to do with those things. So let me put a box around that. So if you remember, if I look at this equation, I have H plus and I have H2O, right? When we see H plus, we know that it's acidic conditions. And that's basically why the H plus is written there to start with. And the water you could ignore to begin with as well. Now, if you saw OH minus in there, that would mean it's basic conditions. I'll take a look at one of those in just a sec. So the best approach when you're doing these is to ignore these to begin with. And just start with the reaction without those in it. Because if you leave those in it, it may kind of confuse you along the way as to what you're supposed to be doing. So if we take those out of this reaction that was given to you, you are left with MnO4 minus plus SO3 2 minus goes to SO4 2 minus and Mn2 plus. So this is probably what you want to start with. Again, I'll explain why these are here in just a second. But mainly here, they're here to tell you it's acidic condition. So we're going to balance this in acidic condition. So that means we're going to split it off into our half reactions. We're going to take the two things that look alike. And the other guy is this. We could also figure out what is going on in terms of oxidation numbers. Oxygen here is -2. There's 4 of them, which is -8, which means that the Mn in this case is actually +7. +7 and -8. Let me say that right. +7 and -8 gives us -1 overall. The oxygen here is -2. And the sulfur in this case then would be, that's -6. Sulfur would be +4 in this case. Coming this way, the oxygen is -2. That's -8. The sulfur here would be +6 in this case. And this guy would be +2. So this is assigning our oxidation numbers like we talked about in class. Again, you could look at your number line there. And we see that the Mn started at +7 and ends at +2, going in this direction, which means it is going through reduction. While the S in this case started at +4 and ended at +6, going in that direction, which means it's going through oxidation. So you could see by using our number line, we could figure it out. We could also see the oxygen, -2 and -2. Nothing happened really with the oxygen. So in this case, what this means is this is our reduction half reaction. This is our oxidation half reaction. That also would mean that the MnO4 would be our oxidizing agent, and the SO3 2 minus would be our reducing agent in this particular case. So what we want to do now is what we talked about before. We want to balance everything other than oxygen and hydrogen. 1 Mn here, 1 over here, so that's good. 1 sulfur here, 1 sulfur here, so that is good. The next thing we want to do is add water, again, to balance out the oxygen. So when we look at the top half reaction, there's 4 oxygens on the left, none on the right, which means the right-hand side should get 4 waters. Because I added 4 waters here, I want to add 8 H pluses over here. Now, on the bottom, we have 3 oxygens on the left 4 oxygens on the right, which means the bottom guy needs 1 water on the left to balance out the oxygen. And because I added the 1 water, I need to add 2 H pluses over here to the right-hand side to balance it out. Any questions up to that point? So now I have balanced everything in terms of their elements. We want to balance out the charge by adding electrons. So on the top reaction, I have 8 times plus 1 is plus 8, and a minus 1. That gives me really a plus 7 overall here. Right-hand side, I have plus 2 and 0. Gives me a plus 2 overall. Again, here, we're going to add negative electrons. We want to get these numbers to equal the same. And that means that we need to take 5 electrons on the right-hand side. So we're going to add 5 electrons over here. 5 electrons gives me 5 negatives. So negative 5 and plus 7 gives me plus 2 overall. Matches my plus 2 that I have on this side. Also makes sense because this is the reduction half reaction. My electrons are on the reactant side, so I'm all good there as well. Now on the bottom, overall charge on the bottom is 0 for the water, minus 2 for the sulfite, minus 2. Overall charge on the right-hand side, minus 2 from the sulfate, and plus 2 from the H+, that is 0. That means that to balance it out, I need to add 2 electrons to the bottom side. That now gives me minus 2 here and minus 2 here, and we are balanced. Any questions on that so far? All right, now that it is balanced, we want to add both half reactions together. But as we talked about, before we could add them together, we do need to make sure that the electrons are the same number in both half reactions, which they are not in this case. I have 5 in the top one, 2 in the bottom one, which means to the top reaction, I need to multiply everything by 2. To the bottom reaction, I need to multiply everything by 5. The purpose of that is to give me the same number of electrons in each half reaction. So I'm going to rewrite both of them. So starting on the top one, I'm going to multiply that 2 to everybody that's there. For the top half reaction, that will give me 10 electrons plus 16 H pluses plus 2 MnO4 minus gives me 2 Mn2 plus 8 waters. Again, all I did was distribute that 2 all the way across. I'm going to do the same thing on the bottom. I'm going to distribute the 5 all the way across. When I do, that will give me 5 waters plus 5 SO3 2 minuses. Gives me 5 SO4 2 minus plus 10 H pluses and 10 electrons. I am now ready to take these both and add them together. What I'm going to do is basically cancel out things that are on the opposite sides of the arrow but are exactly the same. So electrons we know for sure should completely cancel. They're on opposite sides and exactly the same. We actually have 10 H pluses on the right. We'll cancel out with 10 of these on the left, which will give me 6 H pluses that are left over. We actually have 5 waters on the left that will cancel out with 5 waters on the right and leave me 3 waters on the right-hand side. And I think that's all the canceling. So what is left is 6 H pluses plus 2 MnO4 minus plus 5 SO3 2 minus. That is everything on the left-hand side of the arrow. Now we're going to do everything on the right-hand side of the arrow, which is 2 Mn. Try that again. Try that again there. So that is 2Mn2 plus 3 waters that didn't completely cancel, plus 5SO4 2 minus. Now, if I did this correct, we should be balanced both ways. And if we look at it, we have 6 H's on the left, 6 on the right, 2 Mn's on the left, and 2 on the right. Oxygens, we have 8 oxygens here and 15 more. It's a lot, but 23. That is 20 oxygens there, plus 3 more here is 23. And what else we got there? Sulfur, 5 sulfurs on each side. That's a 5 and a sulfur. Overall charge on the left is plus 6 for the H pluses, minus 2, which gives us plus 4, and minus 10 gives us minus 6. We got plus 4 here, and minus 10 gives us plus minus 6 on the left and the right. So we are balanced both ways. So this would represent the balanced equation in acidic conditions. If it was basic conditions, this would be the point where you would add, in this case, 6 OH minuses to both sides. But it was not basic conditions for this one. It was acidic conditions. First off, any questions on any of that there? So now that we have the properly balanced equation here, if we look back at the original equation that was given to us, which was up on top, what we see is the H plus that we ignored to begin with was on the left-hand side, and looky, the H plus is on the left-hand side. The water that we were given originally is on the right-hand side, and look, the water is on the right-hand side. So he put it in there, I think, to, at the end, when you're done balancing it, that you just put the coefficients in front and probably make it easier to grade. But it kind of messes people up because they try to use it from the beginning, and you really shouldn't use those things. So, and all these ones that are on this study assignment, where you see the H plus on one side and some water on the other, you should ignore it until the end. But you can use the original equation to check yourself like we did here. We did get the H plus on the left-hand side, which is where it should have been, and the water is on the right-hand side where it should have been. So I would ignore that. In most cases, what you would be given would be what we started with here. And in a lot of cases, they'll just write like acidic next to it. And instead, he kind of did that. So let me just look real quick here. 2E, for example, if you look at 2E, you have this equation, which is bismuth plus water given to you, MnO4 minus Bi3 plus MnO and OH minus. So this would be an example of a basic condition. I know it's basic because I see the OH minus in the equation, and again, our water. So this, again, for the purposes of the study assignment, will tell you it's basic conditions. And what that means is, just like we did on the other one, I would ignore it at the beginning and start with just a reaction that looks like this. And then obviously at that point, you could do like we've been doing, split it off into its half reactions. Obviously, figure out the oxidation states of everybody, figure out what's being oxidized, reduced. You could add your waters, your H pluses, your electrons, and then at the very end, you will add your OH minuses to both sides. So in this study assignment, it's probably the only place where you'll see it kind of written like this. He sort of included, you know, kind of like this stuff here to indicate that it's basic conditions, but you should kind of get rid of it, then balance it. And in the end, when you balance it, basic conditions, you should end up with OH minus on the right-hand side in this example and H2O on the left-hand side. Any questions on that there? And I think that should take care of most of that there. All right. So again, basic conditions, just like what we did. You want to do tomorrow? Why don't we make it due right now? Upload right this second. No, yeah, you could turn it in tomorrow. Obviously, it's going to take some time to do these. Okay, any questions on that? So obviously, it's good practice to do these. If you need more room, then obviously what's on the study assignment there, you can obviously use a separate piece of paper if you want or something like that. It's fine. And I was going to actually make it due tomorrow. So it will be due tomorrow at the end of lab. And other than that, any questions on any of this stuff? Okay. So this is something, again, technically you are responsible to know for exams and stuff like that. So even though we sort of covered it here, being able to balance these type of reactions is something that you do need to know. And obviously it's a whole study assignment on it. And tomorrow's experiment, which has to do with oxidation of iron, may require you to do some of this type of balancing as well. All right, so officially it will be due tomorrow. Please work on it for the rest of the time. If you have any questions, please feel free to